All right, so on to quantum mechanics. So we know electrons and atoms can exist only in discrete energy levels, and they cannot exist in between the energy levels. The energy of an electron in an atom is quantized. So the energy can be equal only to a certain specific values, and electrons can jump from one energy level to another, but not transition smoothly in between energy levels. So we know the energy levels are referred to as quantum numbers. So the energy levels are labeled with an n value of n equal to 1, 2, 3, etc. Generally speaking, the energy of an electron in an atom is greater for larger values of n. So the further the electron is away from the nucleus, the larger the quantum number, the larger the energy associated with that electron. N is referred to as a principal quantum number or shell number. The principal quantum number defines the location of the energy level and is similar in concept to the Bohr model. So here we see a picture of an atom that has a nucleus, and it has different energy levels that are represented by different circles here. The circle that's closest to the nucleus has a quantum number of n equal to 1. It has the lowest energy value. The second circle has an energy value of 2, n equal to 2, or a quantum number of 2. It has more energy than n equal to 1, but less than n equal to 3. And then, of course, n equal to 3 has the highest energy value in this example. So each energy value or energy level is referred to as a shell. Okay, so here we have 3 different shells that represent this atom. All right, so what are orbitals? So atomic orbitals, the principal quantum number is the one of 3 quantum numbers used to characterize an orbital. So an atomic orbital is a general region in an atom that an electron is most probable to reside. An atomic orbital is distinct from an orbit. The quantum mechanical model specifies a probability of finding an electron in a 3-dimensional space around the nucleus. Okay, so when we talk about orbitals in an atom, basically we're talking about an area in which an electron is most likely to be found. And there are, higher powered mathematical calculations that can go into this. So I wanted to give you sort of an example of what an orbital is. I'm going to draw out, or if I had an orbital, if I were an electron and I had my own orbital, and you were to try to track me throughout the week. Okay, so I'm here right now at home. This is Sunday and then this is Monday, so you're just tracking me, my location. Then Tuesday, Wednesday, Thursday around the school here, and then Wednesday go to DSC. Then I go back home, and then I repeat this process over and over again. So this is sort of what my orbital would look like throughout the week. So the probability of finding me in this region here is very high. The probability of finding me in Calhoun, very small, okay? I'm going to be somewhere in this area. This is my orbital for the week, all right? So when we're talking about electrons, because, an atom's, a very large atom can, has a lot of different electrons. We're trying to figure out the areas in which the electrons can be found. Why is that important? Well, when you have a very large atom, we talk about bonding, for example, covalent bonding, you have an overlap of orbitals. So if you have a covalent bond between two atoms and they have a very large number of electrons as well, two electrons have to occupy the same orbital. So the orbitals are going to overlap to form that covalent bond. And so this theoretical stuff helps sort of scientists understand, more importantly, bonding concepts. Why do certain, for example, when you get into organic chemistry, the question is going to be, why do you have hydrocarbons here that have very similar bonding, for example? And then the question becomes, well, why? When I have this chemical reaction, maybe why is it reacting with this hydrogen and not with this one here? Okay, or here, but not here. So, you get into this theoretical idea. And so this, there's use for this, but we're not going to get into very specifics about applications for it. But the general idea is trying to figure out where the electrons are, because, once you understand that, then you can go and solve more complicated problems in industry and in research. So that's the idea, the general idea behind it. All right. So we talk about quantum numbers. Sometimes I like to sort of warn you before we go into it. So when we're talking about quantum numbers here, we're talking about 4 unique numbers for every electron in an atom. So we talked about N being energy level, or quantum number. All right, or shell is referred to as a shell. Okay. So next we're gonna talk about L, N sub L, and N sub S. Okay, and I don't want to jump ahead of myself, but this is kind of helpful here. It really sort of, if you wanted to think about it in terms to simplify it in a way, we have the shell for an atom, which is a certain energy level. There are a lot of electrons on the shell. Okay, and then we're going to whittle it down. So we're going from large to medium to small. All right, so a shell's, has a lot of electrons. A subshell has a smaller number of electrons. Okay, and an orbital can only have 2 electrons. Okay, so we're getting to that point here with quantum numbers. Okay, because N is the shell. L is going to tell you the subshells. Okay, at that energy level. Okay, and then the orbital is sort of like it's sort of like a small area. It's you can only have 2 electrons in that orbital. All right. Well, I can sort of like describe it like this. When I lived in graduate school, I lived in an apartment complex. B3. Okay, so this was part of my address. This was Fayetteville, Arkansas. All right, so everybody in that complex had this part of my address, 705 West Putman. Okay, so that's sort of like the shell. Okay, so at a certain shell, you have a lot of electrons that have the same energy level. And then the B, apartment B, that was the building number B. That's sort of like the subshell. So some people even had an address of 705 West Putman, apartment B. Okay, so a certain number of people had that. So there's some similarities there. So subshells, you have, fewer electrons in a subshell than in a shell, but more than that of an orbital. Okay, so the orbital you can equate to the actual apartment number. Okay, the apartment number, there's only one person living in there, so one electron. Okay, at one point I did have a roommate, so 2 electrons, 2 people, whatever. But this kind of tells you kind of how this plays out in terms of number of electrons in a shell versus a subshell versus an orbital. So we're going from large to small here. Okay. So orbitals can basically have 1 or 2 electrons, a maximum of 2. Okay, and then with subshells, it depends on the subshell type how many you can have. And then with shells, it depends on the shell how many you can actually have as well. Okay, so we'll talk about the restrictions there. All right, so going back to our notes here. So the principal quantum number is one of 3 quantum numbers used to characterize an orbital. An atomic orbital is a general region of an atom that an electron is most probable to reside. An atomic orbital is distinct from an orbit. The quantum mechanical model specifies the probability of finding an electron in a 3-dimensional space around the nucleus. So I showed you what my orbital would look like if I were an electron. So the next quantum number we're going to learn is referred to as L. That's the angular momentum quantum number. It's an integer that defines the shape of an orbital. Okay, so L can take on the values of 0, 1, 2, 3, and so on. And to find L, you just take n minus 1. Okay, so for an orbital with n equal to 1, the L is going to be n minus 1, or 1 minus 1, which is 0. For an orbital with n equal to 2, L is going to be n minus 1, or 2 minus 1, which is 1, and then you go back to 0 as well. So it's always going to be n minus 1, and then you list the numbers including 0. You go down to 0, and then don't go past 0. All right, so let me give you some more examples here. So if I have an n equal to, or an L equal to, let's say n equal to 5. So L is equal to n minus 1, which is 4, and then 3, and then 2, and then 1, and then 0. If L is equal to 2, or if L is equal, if it is equal to 2, this can be 2, 1, and 0. That would be n equal to 3. L is equal to n minus 1. So there's 3 minus 1, which is 2, then 1, then 0. These numbers all mean something. Okay, they're not just numbers. All right. So L represents the subshells. All right, so we'll talk about the subshells in just a minute. So orbits with the same value of L form what's called the subshell. Okay. So this is something you have to memorize. It's not very hard because when we start to look at our periodic table, this is going to bring everything. Hopefully you'll be able to understand this better. So instead of using numbers, the angular momentum quantum number is often designated by letters. So for an L equal to 0, it's referred to as an s orbital. L is equal to 1, it's p. L is equal to 2, it's d orbital. And L equal to 3, it's an f orbital. Okay. So going back to our example here, if n is equal to 5, L is equal to 4, 3, 2, 1, and 0. So the 0 means that's an s orbital. Okay, and then 1 means it's a p orbital. And then 2, it's a d orbital. 3, it's an f orbital. Okay, and then I don't think we get past f. Although theoretically, you can get past F, but I don't want to blow your mind yet. All right, so I wanted to show you, I really want to relate this to your periodic table because this is going to make it makes more sense when you can look at your periodic table. And I normally teach this using electron configuration before, not after teaching quantum numbers, but I decided to risk it and do it like they have it here. But I wanted to show you, this is a figure we're gonna see later when we talk about electron configuration. You're gonna be bombarded by a lot of numbers. Oh my God, I have to memorize these numbers. But if you look at your periodic table, you can sort of figure this out. Okay, this is a color-coded periodic table. It's color-coded based off subshells. Okay, so we're talking about L subshells, which represent the subshells or the orbitals. Okay, so here we have the first two columns in the periodic table are color-coded blue. Okay, this is the S subshell. You see that here, S. How it's written, 1s, 2s, 3s. The 1 indicates the quantum number, the energy level. This is the first row, so it's energy level 1. This is the second row, it's energy level 2. Third row, energy level 3, and so on. So you see that we have up to 7 energy levels on the periodic table. S is the subshell for the first two columns here. It's color-coded. The exception here, helium is also an S orbital. Its second electron is in an S orbital here. All right, now we said S and then we said P, right? So an L value of 0 is S, an S subshell, or S orbital. A P, an L of equal to 1 is a P subshell. So you can see the P subshells are color-coded here. All right, so you notice there are 6 elements here. So when we're talking about electrons, I know these are elements, but when we talk about electrons, I want you to think of each element as an electron. Okay, so you notice here it has 1, 2, 3, 4, 5, 6. So it's the first electron in the P subshell, second electron in the P, third electron in the P, and so on. And again, the rows match up to be the same. So second row, 2P, third row, 3P, fourth row, 4P, etc. All right, so there's 6 electrons that we can fit here in the second energy level, or quantum number 2, in the P subshell. Here, you're only 2 for each S subshell. See that? And then for D, there are 10 going across there. You see it's numbered 1 through 10 for D. Now, D is a little bit different in the energy levels. Even though this is the 4th row, for D, it starts at 3, energy level 3. Okay, and that's just, there's no way of rationalizing why that is. It's different. D is different. So it starts at 3 and not 4, even though the other ones are 4. All right. And then for F, the F subshell, there's 14 electrons across there, 14 elements, each element representing an electron, because you can think about it, the atomic number is the number of electrons or protons. So we're basically counting electrons here in this 4F subshell here. All right, so here we see 14 electrons there that can occupy each F subshell. Okay. All right, so I wanted to show you that so you know kind of when we're talking about S and P and D and F. So S has an L of 0, P has an L of 1, D has an L of 2, and F has an L of 3. So how do we get those numbers? Well, if you go from the top to bottom, so if we start at the first element on the periodic table, hydrogen, its first electron there, okay, it has just an S. The first whole period here of an N equal to 1 only has 2 electrons there, right? 2 elements, 2 electrons. And then they're in the S subshell. So they come first, so they're assigned a number of 0, L equal to 0. And then the second energy level, you have S and you have P, right? So you go from lithium, beryllium, and then boron. So you have S and P subshells. So P is 1, L equal to 1. So we have 0, we have 1, and then D is 2. And then finally, when you get to F, it has an L of 3. Okay, so that's why the numbers are the way they are. And if you just look at the periodic table, you can remember what comes first, because S comes first, and then P, and then eventually you get to D, and you kind of have to keep on going till you get to this point, and then you go to F. Okay, so it's 0, 1, 2, 3, or S, P, D, and F. All right. Okay, so let's go back here to where we're talking about these things. So hopefully now you have a better understanding of angular momentum and quantum numbers, what L really represents. Now, they're orbitals and they have certain shapes. So when I show you the shapes, hopefully this will make it even easier to understand. All right, so with radial nodes, we talked about this when we talked about standing waves. So there are certain distances away from the nucleus at which the probability density of finding an electron located in a particular orbital is 0. The value of the wave function psi is 0 at this distance for this orbital. Such a value of radius r is called a radial node. So at a radial node, you have 0 chance of finding an electron. All right, so the number of radial nodes in an orbital is n minus L minus 1. So for a 1s orbital, n is equal to 1, then L is going to be equal to n minus 1, or 0. So the number of nodes would be 1 minus 0 minus 1, which is equal to 0. For a 2s orbital, n is equal to 2, L is equal to 0. So the number of nodes there is n minus L minus 1, or 2 minus L, which is 0 minus 1, which is equal to 1. And for the 3s orbital, n is equal to 3, L is equal to 0. The number of nodes are 3 minus L, which is 0, minus 1, which is equal to 2. All right, so we can see that better when we see this picture here. So here this graph shows the probability of finding an electron for a 1s, 2s, and 3s orbitals as a function of distance from the nucleus. And you can see here for the 1s orbital, you have the probability density right here of finding an electron at a certain value, certain distance in picometers away from the nucleus. Okay, so you have one peak there. And then here for a 2s, you have that one peak for the first orbital and then another one for the second one. And for 3s, you have 3 peaks. It's the probability of finding an electron in this area here is higher than, say, over here, over there. Right, and so that's what this graph is showing you. All right, so the S subshell has a spherical shape. Okay, it's almost like, you have to remember too, even though it looks like a sphere, it's hollow inside. It has the nucleus inside. It's almost like the candy-coated shell of an M&M. Okay, if you took out all the chocolate, you had just the shell, that would represent an S subshell and how it looks. It's three-dimensional. It has thickness, but it's not like, well, even like a ball, a rubber ball. If you had a rubber ball, the air inside, there's space inside of that ball. So kind of like a rubber ball, for example, that would be the shape of an S subshell. The P subshell has a dumbbell shape to it, and it's a little bit more complicated. I think they look like either flower petals or maybe the propeller from an airplane. And D and F orbitals are way more complicated because you have a lot of different electrons that can fit in this small area, and so there are a lot of different weird shapes in order to occupy the space, the minimum amount of space that's available around the atom. So these shapes represent the three-dimensional regions where the electron is most likely to be found, and so here we see the shapes of the S, P, D, and F orbitals. I'm going to zoom in as best as I can here. So here's a shape for an S. Orbital here is three-dimensional. It's really hard to see that, but it just looks kind of like a sphere. And then p orbitals are sort of like dumbbell shape. And so you notice there are 3 dimensions there, x, y, and z. Okay, so you have x, you have y, and you have z. And then when you get to more complicated orbitals, notice too something about this. S, there's 1 orientation here. For p, there's 3. For d, there's 5. Okay, let me zoom in here. I told you it would look weird. So we have these different orbitals, okay, in d subshell. Okay, there are 5 different orientations possible. And then for the F, there are 7. Okay, 7 possible. And the orbitals there look even more interesting. Okay, so 7 there, 5 for D, 3 for P, 1 for S. Okay, that's again something you have to memorize, but it's easy to figure out how many there are. Remember, I told you that only 2 electrons can fit in an orbital. So let's go back to our periodic table and count the elements here. So I told you there are 2 elements, right? Or 2 electrons that can fit in the S subshell. So 2 divided by 2 is 1, right? So didn't we see just 1 orientation for an S subshell? Because every orbital for S can only have 1 orbital. And so you only have 2 electrons in the S subshell. So only 2 of them can occupy the S subshell. And then for P here, the P subshell, there's 6 electrons, right, that can fit a maximum of 6 in the entire P subshell, 6 of them, right? So 6 divided by 2 is how many? 3. So that's why there are only 3 orientations for the P orbitals, because each, 1, 2, 3, 4, 5, 6, you can have 6 electrons there total. Okay, but only 3 orbitals, because you can have up to 2 electrons in each orbital. 2 times 3 is 6. All right, and then for D, there are 10 electrons across there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 divided by 2 is 5, right? And so we said there are 5 orientations here for D. Okay, 5 times 2 is 10. So you have 10 electrons, okay? All 10 can occupy, 2 can occupy an orbital, and so up to 5 orbitals in the D subshell there. Okay, and then F, there are 14 electrons. Okay, 14 elements across there, each element representing 1 electron, 1 additional electron. So 14 divided by 2 is 7, and so that explains why we see 7 orientations here for the F subshells, okay, because each orbital can only occupy 2 electrons. 7 times 2 is 14. Okay. All right, so now that we know what the shapes of the orbitals are, we know how many electrons we can fit in each subshell, right? Because all we have to do is just count them. Only a maximum of 2 in an S subshell, a maximum of 6 electrons in the P subshell, a maximum of 10 electrons in the D subshell, right? There's 10 across there, and a maximum of 14 electrons in the F subshell. Okay, how many orbitals? Well, 2 divided by 2, 1 orbital for S. 6 divided by 2, 3 orbitals for P. 10 divided by 2, 5 orbitals for D. 14 divided by 2, 7 orbitals for F. All right. So we need to learn, we talked about L, we talked about N, the quantum number, L, the subshells, and now we need to talk about the magnetic quantum number, M sub L. So if an orbital has an angular momentum, L not equal to 0, then this orbital can point in different directions. The magnetic quantum number m sub L specifies the orientation of the orbital in space. Okay, so the value of m sub L depends on the value of L. So m sub L is equal to negative L to 0 to positive L. There are 2L plus 1 orbitals with the same L value. So one s orbital for L is equal to 0, 3 p orbitals for L is equal to 1, 5 d orbitals for L that's equal to 2, and 7 f orbitals is an L equal to 3. Okay, so we already talked about an L of 0 has an s orbital, and L of 1 has a p, and L of 2 has a d, and L of 3 has an f. When we talk about m sub L, we're talking about the orientation, okay, of the orbitals, which we really looked here at the orientations. Now, this is all going to tie together in just a moment. So, okay, so when referring to an orbital, usually both the n value and the letter designation for L are reported. So when we saw in the periodic table, it gives you the quantum number 2 in the orbital shape S. 3p tells you n of your quantum number and your subshell designation, basically. In the case of a hydrogen atom, energies of all the orbitals with the same n are the same. So this is called degeneracy, and the energy levels with the same principal quantum number n are called degenerate energy levels. So for example, if I only have 2 electrons in an s subshell, right? So if I have both electrons that are in the 2s subshell, both those electrons have the same energy. That's referred to as degenerate energy, or they have degeneracy because they have the same value in terms of energy. The same thing with 3p electrons. Now, with 3p electrons, you can have up to 6 electrons, right, that are designated 3p. But again, their energy levels are all going to be the same because they have the same quantum number, 3. Okay, and they have the same subshell, p. Okay. So, however, in atoms with more than 1 electron, this degeneracy is limited by electron-electron interactions. So orbitals that belong to different subshells have different energies. So an S and P subshell have different energies. Even though if I have a 2s and a 2p, they have the same n values, quantum numbers, but the S and P are different in terms of energy level. Orbitals with the same subshells are still degenerate and have the same energy values. So within the p subshell, they have the same energy level. But if you're comparing 2 different subshells, S and P, they're different. Okay, they have different energy levels. So this figure sort of explains that. We can see here how we have an increase in energy. Okay, so we're starting out with 1s. This is showing you the energy level value for 1s electrons. And you notice that it has the lowest amount of energy. We compare that to a 2s electron. Well, what's the difference? They both have the same subshell type, but the quantum number is different. So 2s electrons are going to have more energy than 1s electrons. 2p versus 2s. Again, the larger the L number, the higher the energy. So S has lower an L value of 0, P has an L value of 1. So P is going to have a higher energy than an S subshell would. Even though they have the same quantum number, the subshells are different. Okay, D has higher energy than P or S. Okay, its L value is 2. Okay, so it has a higher energy level. Okay, and so that's the relationship between quantum numbers and subshells and energy and how they're related. So again, electrons that have the same quantum number in the same subshell, all these electrons, notice the lines are, they're on the same plane here because they're all degenerate in terms of energy. The energy is the same between the electrons. They all have the same amount. All right, and then finally, the spin quantum number. So spin quantum number, of course, we've already learned three different quantum numbers, n, L, and m sub L. They define the region of space where the electron is most likely to be located. The last number we're going to talk about, m sub s, is referred to the spin. So electron spin is a different kind of property. Electron spin describes an intrinsic electron rotation or spinning. An electron can only spin in one of two quantized states.